Let's answer this question. Pause until you've tried it yourself. We're going to be applying our knowledge of physical properties of organic compounds to answer these questions. The first step is to make sense of the information that we've been given in the table. Convince yourself that these are the correct structures for 1-chloropropane and 1-chlorobutane. 1-chlorobutane has a higher molar mass than 1-chloropropane, which makes sense since 1-chlorobutane has a longer carbon chain. Explain why the longer 1-chlorobutane has a higher boiling point. Although there are various kinds of intermolecular forces which exist between these molecules, it's the London forces which are responsible for this trend. Explain the difference between these two molecules by writing the relevant word in red on each line to refer to the shorter 1-chloropropane compared to the longer 1-chlorobutane. The shorter 1-chloropropane has less surface area over which the London forces can act and therefore weaker intermolecular forces, meaning that less energy is needed to break these forces, resulting in a lower boiling point because of a higher vapor pressure at a certain temperature, compared to the longer 1-chlorobutane. Consistent with this, the shorter 1-chloropropane has a boiling point of only 47 degrees Celsius, whereas the longer 1-chlorobutane has a boiling point of 78 degrees Celsius. So now we can answer these questions. 3.1. These compounds are all haloalkanes. 3.2.1. The intermolecular forces responsible for the difference in boiling point between B and A are London forces. 3.2.2. B has a higher molar mass associated with a longer chain length, therefore a greater surface area, therefore stronger London forces, therefore a higher boiling point due to a lower vapor pressure than A. Or you can give the answer the other way around, as done here. Now let's compare B and C. 1-chlorobutane and 2-chlorobutane. Both have the same molar mass. The difference between them is the positioning of the chloride group within the chain. Because of this difference in the position of where the chloride group is, there's a bit of a difference in symmetry of the molecule, and that causes one of the molecules to have a stronger and the other a weaker dipole. To help you to think about this, write one of the red words on each line referring to B compared to C. B, 1-chlorobutane, is more asymmetrical than C. Imagine if you would cut each one in half. C is more similar on either side of the cut, so C is more symmetrical. B has a greater difference on either side. It is more asymmetrical. And the more asymmetrical a molecule is, the more polar it is. In other words, the stronger the dipole. Stronger dipoles have stronger dipole-dipole or dipole-induced dipole intermolecular forces, which explains why B has a higher boiling point than C. Question 3.3 asks us what type of isomers B and C are an example of. They are positional isomers because they differ in the position of the halide group within the chain. So now let's compare C and E. 2-chlorobutane and 2-chloro-2-methylpropane. Both of them have the same molar mass, but how do they differ? E, which is 2-chloro-2-methylpropane, is more branched than C. How does that affect the strength of the London forces between them? To help you to think about the situation, fill in the red word on each line to describe the less branched 2-chlorobutane compared to the more branched 2-chloro-2-methylpropane. Compared to the more branched 2-chloro-2-methylpropane, 2-chlorobutane is less branched for the same molar mass, and therefore it offers more surface area for London forces to act, resulting in stronger London forces and therefore a higher boiling point because of the lower vapor pressure at a particular temperature. Consistent with this, the more branched compound E has a boiling point of only 51 degrees Celsius compared to C's 70 degrees Celsius boiling point. Question 3.4.1 asks us to predict what the value of N will be if it must be one of the options given here. To answer this, we're going to compare A and D and then C and D. See if you can first do this on your own. Make sure you answer in a full manner that's going to get you all your marks. First, we compare A with D. We can see that D has a higher molar mass than A. We also notice that D is more branched than A, but be careful about this because the effect of branching on boiling point only applies for similar molar masses, which is not the case here. Try to explain what you can deduce from a comparison of A and D's molar masses on your own first. To help you complete these sentences comparing D to A. D has a higher molar mass than A, and therefore D has a greater surface area over which London forces can act, resulting in stronger London forces, making the boiling point higher for D than A. From this we can conclude that N must be, you complete the sentence, N must be higher than 47 degrees Celsius, which means that 45 degrees Celsius is excluded as an option. Now we compare C with D. Try to go through a similar reasoning process on your own to determine and explain the final answer. Use this guide if you couldn't manage alone. D is more branched than C. As a result, D has a lower surface area over which London forces can act, resulting in weaker London forces and consequently a lower boiling point than C. What can you conclude from this about N? N must be less than C's boiling point of 70 degrees Celsius. Therefore, 80 degrees Celsius has been ruled out, leaving only 69 degrees Celsius as a possibility.